So, hello everybody to this third lecture of my series on computational representation theory. In the first two lectures, I have told you about characters. In the first lecture about ordinary characters and how to compute them with a computer. And in the second lecture about Brauer characters or modular characters and some ways of finding the Brauer character table in easy and small cases, in particular for p-solvable groups if the characteristic of the field you are working over is p. But the computations were all with characters, so with functions or class functions defined on the group and with values in the complex numbers, or rather in a finite extension of Q, a cyclotomic extension of Q. Today, I'm starting 2 lectures or 3 lectures, which will tell you how to compute really with representations themselves. And to put this into a more general context, because it is used like this and it's done like this and it works in this general context, I will tell you about representations of groups I have already told you about, and algebras. And the second part of the lecture will be the MEATAXE, which is a method of dealing with representations of groups and algebras. Okay, again, G is a finite group and F a field. And this has already been the topic of other talks, the group algebra. Let me just recall what it is. It's a finite dimensional algebra. The elements are formal linear combinations of the group elements. You can think of it as a vector space over F, which is finite dimensional and which has the group elements as bases. So it's a finite dimensional vector space, but you can multiply these elements by extending the multiplication of G in a distributive manner. So this is a finite dimensional F algebra. The dimension is the order of G. Okay. To be even more general, what is a representation? In a very general sense, a representation of G is an homomorphism, a group homomorphism into the automorphism group of some object. So this is the most general notion of notation I can think of. And this explains why groups are so important and central, because categories are central. I mean, categories are a way of defining mathematical theories. And once you have a category, you have automorphisms of objects, symmetries. And so this is a way of comparing a given group with the automorphism group of some object, like a manifold or a vector space. Okay, we will mainly look at 2 categories: finite dimensional vector spaces over F, and the automorphism groups are, of course, the general linear groups of vector spaces. This gives you what I have called linear representations, or what I have called representations in the first 2 slides. And another sort of representations of the group is if the objects are finite sets and maps between them, then you get permutation representations, because the automorphism groups in this category are just the symmetric groups on these finite sets. But it's a group. Yeah. Yeah, I think so. Well, you can think of categories where you have some. Well, I think in my definition, the morphisms between objects and categories are sets. In my definition of a category. So the automorphism of an object is a subset of the set of all morphisms between Z, and it's a group. But of course, I think there are more general categories. Well, okay, yes. An F representation, as you recall, is a group homomorphism from G into GLV. And we want to make an FG module out of this representation. And this is just by forgetting about all these symbols used to write down the representation. So we just write V dot G for the vector obtained by applying the automorphism X of G to the vector V. So this is just an abbreviation of language, but this makes V into a right FG module. So an FG module is just a finite dimensional vector space with a G action, a linear G action, okay? And then you have notions of irreducibility, and it's clear that such a representation is irreducible in the sense I defined it on my first slide, if and only if V does not have any proper G invariant subspaces or no FG submodule. It's a simple submodule. It's a simple module. So, and equivalence of representations is described by isomorphisms of FG modules. So this is just a slightly different language, which is sometimes more convenient than the language of representations or matrix representations, because it, in some sense, it incorporates all basis changes you might want to look at in this notion of module. Okay. What is an algebra? What is a representation of an algebra? So A is a finite dimensional algebra, for example, the ring of all n by n matrices over F, or the ring of all endomorphisms of V. Okay. So now an F representation of this algebra is just an F algebra homomorphism from A into this concrete object, namely the ring of endomorphisms of a finite dimensional vector space. A linear F representation of an algebra. And of course, if you have a group representation, so the representing the elements X of G are automorphisms, but if you add them, you get endomorphisms, so this naturally extends to the representation of the group algebra FG. And then a representation for G is irreducible if and only if this corresponding algebra and representation is irreducible. And again, we can view V as a right A module. So the set of the category of A modules, of right A modules, in a sense, is the same as the category of A representations, representations of A over F. But I'm only talking about finite dimensional modules, only finite dimensional representations. Everything is finite dimensional. V is always finite dimensional. And irreducibility and equivalence are defined as in the case of group representations. So if you have an A module, you can think of the A invariant subspaces, and if there are none, except for the trivial one and for the whole module, then it's a simple module or an irreducible module, and equivalence is just the isomorphism of modules over A. Okay, so this was just a sort of a general introduction into the language of representations of groups and algebras, and you will see why this is what this is good for. First of all, I would like to recall how to construct representations, for example, for a group. Because if you want to apply the MEATAXE, you have to start somewhere. You have to start with some representation. Because, I mean, there's always the trivial representation. If you start with a trivial representation, you can do everything with it you like, but you will always talk about the trivial group. Yeah, you have to start with some representation. And since we want to compute representations of the sporadic groups, we have to start with some representation of sporadic group. This does not need to be a permutation, a linear representation. It can be a permutation representation. And of course, most of the sporadic groups are described in a way or constructed in a way such that people say, well, look at these two matrices, they generate the Janko group J1. Yeah, or look at these permutations, they generate M11. Usually the groups come exactly in this way. An existence proof comes with an explicit representation. So you can use permutation representations. I will just tell you later how this is done, but it's completely obvious actually. You can use Kronecker products of representations. You can find new representations by finding invariant subspaces in a given representation, in a given module, if the module is not irreducible, which usually it will not be if you construct it in some way, and in various other ways like looking at symmetric powers or alternating powers of modules and things like that, which are much too technical to introduce here. So a permutation representation is a group homomorphism into the automorphism group of a finite set, which is the symmetric group of this set. And now you want to linearize this. I mean, you just replace every permutation by the corresponding permutation matrix. Just number the rows and columns by the letters, and then put the 1 in row 1 if the first letter goes to I in column I and row 1, yeah, and so on. So we replace each representing permutation by the linear map, which permutes if you want to think of vector spaces, you choose a basis, number the basis elements by 1 up to n, and then you permute the basis in this automorphism exactly as you permute these letters. So this is a corresponding permutation matrix. It's a matrix which has exactly one in each row and in each column and zeros elsewhere. So this is the natural way to linearize a permutation representation. And notice that, I mean, this works for any field or any ring you can think of. Okay, so let's look at an example. A symmetric group on 3 letters. This is the smallest example somehow which you can put on one slide. It acts naturally on the 3 letters 1, 2, 3. You have 2 generators, A and B, transposition and the 3 cycle. And then we take F equal to Q, just to be concrete. We take rows, since we act from the right. And then you let G act on EI just by replacing it by EI to the G. This is the standard basis. So these are the corresponding matrices. So A is the transposition, so it swaps the first 2 rows. And B is the corresponding matrix you obtain by permuting the rows according to this permutation. So we use row convention because we are acting from the right. Okay, and one point is, of course, in order to store such a representation of the group G on a computer, we don't have to store 6 matrices for the 6 group elements, or 10 to the 54 times 8 matrices for the group, for the elements of the monster. We just have to store 2 matrices for a generating set. Every information, the information about this representation is contained in 2 matrices. And notice that as every finite simple group is generated by 2 elements, you can always do with 2 matrices for every finite simple group. Well, let me put it this way. Every sensible group is generated by 2 elements. Yeah? To contrast Heiko's, yeah. When Heiko gave his talk, I started to, start a group theory of 2 groups of class 2, because most of the groups are like this. So if you study 2 groups of 2 class 2, then essentially you do group theory. Yeah, but of course this is not meant seriously. So my sensible groups are generated by 2 elements. Yeah? A Kronecker product, of course, this can be done with 2 representations. You have a notion of a Kronecker product of matrices. This is just defined as follows. If you have 2 matrices, A with coefficients A, I, J, and a matrix B, a square matrix of some other format, this is a D by D and this is E by E, then you make the block matrix constructed in this way. So this is a D times E times D times E matrix. And if you start with 2 representations of the group G in the way these Kronecker product behave by multiplication, you see that you still get a representation of the group G. Of course, if you want to think of modules or of modules, it's the representation afforded by the tensor product of the 2 modules for X and for Y. It's the tensor product in the usual sense defined over the ground field F. And if you compute the trace of this matrix, you see that it's just the trace of B times the sum of these elements. So this tells you that whatever the character of this tensor product of representations is the product of the characters. So this is what I promised to prove you in my first talk. You have to construct a certain representation which has as a character the product of the characters of the representation we started with. This is the construction. You can look at invariant subspaces. This was on one of my first slides as well. So you look for invariant subspaces, so subspaces which are invariant under all group elements simultaneously, or submodules. And then you get new representations, one on the submodule and one on the quotient module. So once you have found an invariant subspace in a representation, you get new representations. For example, let's look at this example with S3. Since these basis matrices are permuted as the letters 1, 2, 3, you see that the sum of these elements is invariant. And whenever you apply a group element to this sum, you get back the sum. So this gives you a one-dimensional invariant subspace. And now what you can do, you want to see, we choose a basis which goes through this invariant subspace. So the first basis element is this basis element of the invariant subspace, and you extend to a basis of all of B. And then, of course, you see this block diagonal structure. And of course, this vector is fixed by all group elements, which amounts to the 1, which says that it's 1 here, and the representation on this invariant subspace is the trivial representation. Whereas on here, you get a new representation. So you get a new representation by looking at these 2 blocks. And in the computer, the representations are really stored as matrices. So by a base change. Okay, so what you need is you need to find invariant subspaces and basis for them and extend the basis to the whole space to be able to construct as matrices these new representations. Okay, but now of course you can do the same thing. You can ask yourself, here are these irreducible representations? What do you think? Yeah, the answer is, a very good answer is it depends. Yeah. So you can think by yourself, what does it depend on, yeah? Whether or not this is irreducible. It depends. This is always a good answer a student can give. It depends. But then the question is, what does it depend on? And then the answer is not so easy anymore. Okay. So if you iterate this process, you obtain a matrix representation where all these representations on the diagonal are irreducible. And so these are the irreducible constituents or composition factors of the original representation or of the vector space or the module, if you want to think of representation as being afforded by a module. And they are unique up to equivalence by the Jordan-Hölder theorem, which is a very general theorem on such composition series. But if you think about my first lecture where I told you that the characters of irreducible representations are linearly independent, which can be proved before proving the Jordan-Hölder theorem, you can derive a different proof of the Jordan-Hölder theorem from this, because if you had two composition series, you would get exactly the same characters, and the characters of the irreducible representations, they describe the representation up to equivalence. Another fact. Yeah? So you need these two facts. Well, this is my ad hoc notation because I couldn't think of anything else. So this means that at the end of the iteration, yeah, when you cannot go further, but just forget the symbol, it's an ad hoc symbol for the sake of this lecture. Okay, now, if you iterate this process, if you compute F representations from permutation representations, and permutation representations are usually not so difficult to get, from Kronecker products of representations, from various others like inducing representations, which you can also do on a computer, or restricting representations, which you can also do on a computer, or symmetrizing representations. And then if you construct and reduce, and construct and reduce, you will finally obtain all irreducible representations. So this is a theorem. Of course not as it is stated here, yeah. Of course you have to make this more precise. Yeah, but anyway, at least if you have a simple group. Of course, if you have a group which is not simple, and you start with a representation which is not faithful, and you are not careful enough, then you might just only be able to construct all irreducible representations of the group modulo the kernel of the first one. Okay? Like if you start with a trivial representation, you will only construct the trivial representation of the trivial group. So you have, at some stage, you have to have a faithful representation, or at least enough representations such that the intersections of their kernels is trivial. Yeah. But of course, we are only dealing with simple groups, so we don't worry about kernels of representations. Okay, second part of the talk is the MEATAXE. So the MEATAXE is a collection of programs that perform the above tasks for finite fields F, of course for finite groups, and really explicitly with matrices. Explicitly, which means that the matrices cannot be too large. How large they can be depends, of course, on the implementation of the MEATAXE. I would say the standard MEATAXE, which is in gap, can be used for representations, say, up to 50,000 of dimension, maybe. So this is, essentially it goes back to ideas of Richard Parker and John Thackeray, and Richard Parker was the first to implement the MEATAXE, and he has since then implemented many MEATAXes, plural of MEATAXE. So he is still implementing a new one, the MEATAXE 64. MEATAXE 64, which refers to his age, I guess. So his plan is to finish it when he is 64. I'm not sure whether he will achieve this, and this will be the most sophisticated and most powerful MEATAXE ever once it's finished. Well, as I said, many people have contributed ideas. Derek Holt and Sarah REES have contributed a very nice idea. Gabor Ivanyosh and Klaus Lux have solved one of the subtle cases which was not theoretically clear. Jürgen Müller has, I think, written a MEATAXE which works over rational function fields, a rational function field over the rational numbers. Michael Ringe has a very powerful implementation, a standalone C MEATAXE, which is still used, and Richard Parker, as I said, is still developing MEATAXE. Yeah. Okay, what are the basic problems? Suppose you give the MEATAXE a representation, which just means you give it 2 matrices, or maybe 11 matrices over the same field, which do not really need to be invertible. So if the matrices are invertible, they generate a group, and so these are the matrices of a representation of the group they generate. If they are not invertible, they generate in the ring of matrices a subalgebra. So it's a representation of an algebra. How does one find an invariant subspace? Well, first of all, you see it is enough to find a vector which is non-zero and which lies in an invariant subspace. You just have to find one vector which lies in an invariant subspace, which is not zero. Of course, the zero vector I always find. Indeed, if this is, you see, okay, so this is written for groups, but you can as well think of algebras. You see, if this lies in an invariant subspace, all these vectors will also lie in the same subspace, and then their linear span will also be in this subspace, and in fact, they might be even smaller than this subspace, but at least this linear span of these elements is invariant. Just find one vector. And the next, which is even harder, if one tries hard to find such a vector and does never find one for some time, how do I prove that the representation is irreducible? Okay, here are the answers. Okay, now I am in a more general context of D by D matrices over F, so any matrices. So I take the algebra span inside the ring of D by D matrices over F, so this is just a set of all F linear combinations of all products of all the matrices A1 up to AL you can think of. Smallest algebra, F algebra, which contains these matrices and F, of course. And for some reason, I also want to transpose all the matrices, so this gives you a transposed algebra inside, so everything is inside this ring, D by D. So this A is a subalgebra and also A transposed is a subalgebra. This is some sort of dualizing things. Okay. Now we let B be an element in this algebra. N of B is the null space, the kernel. So if B is such an algebra, N of B is the set of all W in F to the D such that WB is 0. The left null space. And then so this is Norton's irreducibility criterion. One of the following cases occurs. Either B is invertible, then the null space is trivial, or there is a non-trivial vector in this null space which lies in a proper invariant subspace. So this is exactly what we want to find. So we want to find non-invertible matrices, and then maybe if this null space is small, we don't have to search for too many matrices, but unfortunately there are the third case. Every non-trivial vector in the null space of B transpose lies in a proper invariant subspace in a transposed situation here, or A acts irreducibly. So you see now, you can see a strategy how to prove irreducibility. Take a matrix in A, well, A1 times A2 plus A1 plus A2, for example, and hope that its null space is one-dimensional. Then you just have to search one vector. Yeah. And then in here, you spin, you try to see what this vector, in which invariant subspace it lies. If it doesn't, then you take the vector in this null space, and if it also doesn't lie in an invariant subspace, you know that it's irreducible. Okay, to prove this I leave as an exercise. This is really very easy, elementary linear algebra. Just think, if you try to prove this, just think that that B is not invertible and that A does not act irreducibly, and then write all these matrices in an appropriate basis, and you see what's happening. And you have two blocks, and then you have to fiddle around with null spaces. Okay, so the basic strategy of the MEATAXE is to find a B by a random search with a null space of small dimension, preferably 1. You will not always be able to find a null space of dimension 1. Well, and for all non-zero vectors in this null space, test if this span, so W dot A, this is just the set of all WA A in A. So this is an A invariant subspace. Test whether it's the whole space. If it is the whole space for all such vectors, just test one vector in the null space of the transposed. If this is also the whole space, then the representation must be irreducible by Norton's criterion. But you see, this test is also very good, because if this test above fails, you get an invariant subspace for free. So at both time you get invariant subspace, so you prove that it's irreducible. Even in this case, I will tell you on a later slide, even in this case, you get, by duality, you get an invariant subspace, which you can explicitly write down if this fails. Well, if you want to apply this for group representations, the AIs you started with are just representing matrices for generating set for your group. So this is more general. The AIs in this criterion or in this strategy need not be invertible. But if you start with a group, they will be invertible. Okay, how do you compute this? Well, this is a lecture on computational methods, so at least I will show you one algorithm. How do you compute this? Well, maybe you remember the orbit algorithm. So if you have a group G acting on a set omega, and G is generated by A and B, and then you want to compute the orbit, what you do is you iterate omega A, and then you look at omega B. So if this is, well, I don't know whether I can do this from scratch. So the orbit is omega, and then the orbit is replaced by omega A if omega A is not in O, and then by omega B if omega B is not in O, until you see it doesn't get larger. You apply in turn the group elements to one vector you start with, and then you apply it to all the new elements you get. And so this is similar. Instead of testing whether this lies in O, you test whether it's linearly independent of the ones you had already found. These are matrices. You put in a vector, and then what you get is a basis of this subspace, which is A invariant. It might be the whole space. So for every vector, so you initiate your basis with a vector W, it was non-zero. And then for I from 1 to L, test whether the new vector which is obtained by applying AI to V, union the vectors you already have, is linearly independent. So it just amounts to test whether this is linearly dependent of the vectors you have. If not, you append it, and otherwise you just delete it. And you see, of course, if you do this until you find no new vector, you will have a basis of an invariant subspace. So now you have a basis. You see, this is the second thing you wanted. You have a basis, and you can transform your matrices according to this new basis, and you find the matrices for the representations on this invariant subspace, if it's not the whole space. Otherwise, well, you haven't gained anything. Okay, so I have shown you how to, at least I have tried to indicate how to prove that the representation is irreducible, and on the way of proving this or disproving it, finding invariant subspaces. Another thing you want to test is, when are two representations equivalent? This can be hard. I mean, if you have characters, you just look at the values and see whether they are equal. But to find matrices which transform one representation into the other can be hard. But you can still use this spinning algorithm under certain circumstances. Suppose you have two irreducible representations of an F algebra, which is generated by these elements. And then you have matrices in the first representation and matrices in the second representations for the generating elements. Now you work in this free polynomial ring. Take a word in the free polynomial ring, such that if you evaluate the word in the generators, it has nullity 1, so the kernel has dimension 1. You may not be able always to find such a thing, but suppose you find such a word, like A1 times A2 plus A1 plus A2, things like that. Suppose you find such a thing. Then you can evaluate the same word with a representation B. Well, if the nullity of this new matrix is not 1, then the two are not equivalent and you are done anyway. So you may assume that both nullities are 1. And now you choose a vector in the null space of the first one and the null space of the second matrix. Both vectors, of course, non-zero. And you have started with an irreducible representation. So the spinning algorithm will spin up the whole space and will find bases. So this is the basis of the spinning algorithm with respect to the first representation and the vector V. This is the basis with respect to the second representation and the vector W. And then you get new bases for your representation. You transform the representations according to these new bases. And then, as you can convince yourself with a little linear algebra, the two representations are equivalent if and only if the new representations are equal, visibly equal. Equal. course, this depends on, it depends on the way that you, that you really apply an algorithm here. So this is the algorithm in the way you always apply the same basis element in the same order to the same new vector, you see. And then if you think about it for a while, you will see that this works. Isn't this great? Well, I think today I will not be too short in time. I will be too short in time anyway. So this strategy works well if f is small. For example, you have to find matrices of nullity, which are not invertible. Of course, if you do this over the real numbers, every matrix is invertible, so you will not be able to find anything. But over the field with two elements, 71% of all T by T matrices are invertible. So by a random search, you will find many of them. But as f gets larger, it gets harder to find suitable matrices B by a random search. And this is what HOLT and REES introduced, a new idea how to find such elements with a preferably small null space, but with a non-zero null space inside the algebra. So how does this work? You take these matrices again. You take the corresponding, you take the corresponding algebras, and now you take any element B in this algebra. It can be invertible. Look at the characteristic polynomial of B, and now look at its irreducible factors. And they call an irreducible factor of such a matrix good if its degree is the same as the dimension of the null space of the matrix you obtain by evaluating the polynomial P at B. So P is an irreducible factor with this property. And then suppose you have found a good factor of this B, and then you take two vectors in the null space of P of B, and one in the transposed, and then the criterion is A acts irreducibly if both of these vectors spin up to the whole space. So instead of finding a lot of non-zero vectors in a large null space, just need two vectors. Just two vectors to spin up. And so what they do is the following modification of the MEATAXE algorithm. Choose a random B in this, compute the characteristic polynomial of B. That is easy. Compute the irreducible factors of the characteristic polynomial. This is usually not so easy, but in the dimensions we work with, most of the time it will be doable. But if it fails, just choose another matrix B until you find the irreducible factors. Now for each of these factors, evaluate B at this polynomial to get a new matrix, and then test whether this factor was a good factor, but don't drop the factor if it is not good, because you still can be lucky. Do the spinning algorithm with one of these vectors in the null space of A. And if this is not the whole space, you return W as an invariant proper subspace. If you are lucky, even if P is not good. But if this fails, so if this spins up to the whole space, then look at the transposed situation and again compute the spin up of this vector. If it's a proper subspace, you get an invariant subspace for the original algebra by looking at this W. So you just take all vectors such that W prime, W transpose is 0 for all W prime in this invariant subspace for the transposed situation. It's just If P is good, and in both cases you have spin up the whole space, representation is irreducible. Okay? Well, and then go back to step 1 until you are fed up with it. Yeah. But this works very well, and this is the MEATAXE that is implemented in Ringe and I think also in GAP. Let me tell you about Rob Wilson's atlas. So this is a huge collection of explicit representations of finite groups. Here's the email address, permutation representations, matrix representations over various fields. So this is very useful if you want to compute your own representation. So if you find, if you have a group and you want to compute its representations, and if it's simple, then go to this atlas to find one representation to start with. So these are representations computed by Wilson and others. For example, there is a representation of degree 196,882. This is not on the website because it would be too large for the computer, but this has also been computed. And the information on this website is also available in GAP through the GAP package Atlas Rep, so it can be just retrieved from the website and put into GAP to work with. This is very useful. So this is what I wanted to tell you today. Here are some references. So this is this handbook and the MEATAXE according to HOLT and REES, and a general book on computational representation theory by Lux and Parlings. And this is the paper where Richard Parker, for the first time, describes his MEATAXE. And tomorrow I'm going to tell you what to do when the MEATAXE fails. So the MEATAXE, the most sophisticated MEATAXE, Ringe's MEATAXE, for example, can maybe handle nowadays on large computers matrix representations of degree up to 200,000 over F2. But we are dealing with matrix representations of degree 300 million. And this is condensation, which does the job for us, and I'm going to tell you about this tomorrow. Thank you very much.